This is the story of H.T.G.R, the high-temperature gas-cooled reactor system for commercial power generation. How it works, its advanced technology and development, and why it holds great promise for achieving in the shortest length of time the goal of economic electric power from the atom. Since early summer 1957, General Atomic, a division of General Dynamics Corporation, has been engaged in development of the H.T.G.R system. The result is a new concept of nuclear power generation. Late in 1958, the Philadelphia Electric Company and 52 other investor-owned utilities accepted the U.S. Atomic Energy Commission's invitation to develop, design, build, and operate a high-performance gas-cooled nuclear power plant. These companies chose the H.T.G.R as a developmental project to advance both the technology and economics of nuclear power in the United States. Organized as High-Temperature Reactor Development Associates, the 53 companies comprise the largest and most widely representative group of utilities ever to support a nuclear power project. Together, these 53 companies account for 42% of all the electric power produced by investor-owned companies in the United States. This is a scale model of the prototype H.T.G.R plant now under construction at Peach Bottom in southeastern Pennsylvania on the Philadelphia Electric Company system. Spectral Corporation is engineer-constructor. When completed in 1964, the 40,000 kilowatt plant will be the world's first all-nuclear power station to produce commercial electric power at modern steam conditions of 1,000 degree temperature and pressure of 1,450 pounds per square inch. The Peach Bottom prototype plant is designed to demonstrate in commercial operation those advanced features which in larger H.T.G.R plants are expected to produce economic power, competitive in cost with the electricity generated in conventional plants which burn fossil fuels. The main steam power portion of the prototype H.T.G.R plant is primarily outdoor type construction. The nuclear steam supply system of the plant is enclosed within a containment shell. As with all nuclear power plants, the heart of the General Atomic H.T.G.R system is the reactor. The reactor core is made up of about 800 cylindrical graphite body fuel elements. Helium gas enters the reactor vessel through the outer duct and flows down the inner wall of the pressure vessel. It then flows up through the core, absorbs heat from the surface of the fuel element, and carries the heat out through the inner duct to the boiler. In order to prove out the coolant flow system, General Atomic engineers conducted extensive tests on a 1/2 scale plexiglass model of the Peach Bottom reactor. The model simulates coolant flow conditions through the core and pressure vessel and duplicates the internal helium coolant paths of the reactor. Engineers investigated in detail such items as flow distribution, pressure drop, and heat transfer. The model's transparent walls permit visual studies of flow patterns by means of smoke introduced into the simulated helium stream. The men conducting the tests are seen here recording pressure measurements indicated by manometers connected to 400 different points on the model. The total test results verified the flow design characteristics of the H.T.G.R. The H.T.G.R is the first commercial nuclear power plant to use graphite-clad fuel elements instead of metal cladding, which wastefully absorbs neutrons and limits operating temperatures. Graphite is an excellent cladding and structural material because it conserves neutrons and its strength increases at higher temperatures. This 1/6 segment of the core was assembled for test purposes at General Atomic. The prototype plant's nuclear core will contain approximately 800 fuel elements, each 12 feet long and 3.5 inches in diameter. An individual fuel element has an upper reflector section, a center fueled section, an internal fission product trap, and a bottom reflector. Within the fuel element, fuel compacts are stacked on a graphite spine. The uranium and thorium fuel within the compacts is in the form of carbides, uniformly dispersed as tiny particles in a graphite matrix. These are the fuel particles, each approximately 1/1000th of an inch in diameter. In this photo, they are, of course, magnified many times. The fuel particles are fabricated from 3 powdery substances: uranium oxide, thorium oxide, and a cellulose binder. Mixing uranium and thorium is a means of conserving fuel supplies and reducing fuel costs. U-235, which is fissionable and expensive, is mixed with thorium, which is 1,000 times cheaper. When U-235 atoms are split, excess neutrons convert a portion of the thorium into fissionable U-233, an even better fuel than U-235. Some of this new fuel is then burned along with the U-235. This helps greatly to extend the lifetime of the fuel elements. Fuel element lifetimes range from about 3 years for the peach bottom to 6 or 7 years for the larger reactors. Fuel fabrication techniques were developed at General Atomic's new fuel and metallurgy facility. Eventually, the operations seen here will be automated, reducing to a minimum the handling of fuel materials. However, during the development period, specially trained technicians guide the particles through the many fabrication steps under rigid production and environmental controls. Coating the particles with a dense but very thin layer of carbon is an important feature of the H.T.G.R. high-performance fuel. Coating is accomplished by suspending the particles on a bed of hot helium and methane gas. The methane decomposes into carbon and hydrogen, and the carbon is deposited on the fuel particle. This coating serves the dual purpose of keeping moisture out during compact fabrication and of keeping fission products in during reactor operation. The thickness of the coating is carefully controlled and constantly monitored. A sample is viewed under a microscope, the coating measured, and a photographic record made for analysis and future reference. In compact fabrication, 1 part of fuel particles is added to 1,000 parts of graphite. The mixture is carefully blended and placed in a die. Hydraulic rams compress the blend, and resistance heaters around the die heat the compact, bonding the homogeneous mass into a solid unit. The high ratio of graphite to fuel achieves 2 purposes. It provides a large area for heat conduction and maintains the structural strength of the compact, even in the ideal case of complete fuel burnup. This is a low-power reactor called a critical assembly, which General Atomic designed and constructed to provide detailed information on the nuclear characteristics of the H.T.G.R. reactor cores. This 25-ton assembly is used to verify calculations on such items as proper uranium-thorium core loadings, control rod efficiency, and change in reactivity in the fuel material with change in temperature. Within this large test reactor, General Atomic designed and constructed what is, in effect, an actual H.T.G.R. pilot plant. The men are loading an H.T.G.R. test element in the reactor chamber. Here, the H.T.G.R.'s fuel elements are tested under the actual radiation, temperature, and pressure conditions of the peat bottom plant. The facility, known as the General Atomic In-Pile Loop, has a fuel element chamber, a closed-loop helium circulating system, a fission product trapping system, and provisions for sampling the helium flow. The development, construction, and testing covered a period of 3 years, and the elements have been subjected to more than 6,000 hours of reactor operation. Radiochemists sampled the circulating helium stream during the test using remotely controlled mechanical hands. The test proved out a number of important features of the H.T.G.R. system: the effectiveness of the fuel element in retaining fission products, the high fuel burnup, and the very long life of the H.T.G.R.'s graphite-clad elements. Following the pilot test, a fuel compact and a section of the graphite sleeve were returned to General Atomic's hot cell facility for examination. This compact showed not the slightest evidence of structural deterioration after 2,000 hours in the reactor. Samples were drilled from the graphite sleeve to be examined for fission product migration. The results were equally encouraging. This is the reactor components test tower at General Atomic. A full-size prototype control rod and its drive mechanism, both designed and engineered at General Atomic, were thoroughly tested under the reactor pressure and temperature conditions of the peat bottom plant. They were subjected to nearly 600,000 starts and stops, far more than expected in the life of a power plant. The control rod that was removed for inspection after the test showed no changes other than minor wear. In this same tower, the fuel transfer mechanism that will be installed in the peat bottom plant also was tested. The 9-ton machine, with its 47-foot arm, inserts, positions, and removes fuel elements to or from any position in the reactor core. A 1/6 segment of the peat bottom plant's core is used to check out the machine's many operating parts. The operator remotely controls the machine from a console which, in the actual installation, will be located outside the containment shell. The grappler head is inserted into the reactor from a guide tube above the core and positioned over the element to be transferred by remote control. In spite of its massiveness, the machine is a precision instrument. Radial motion can be held within 1/100th of an inch and rotation within 1/10th of a degree. This makes possible the precise location of any one of the 800 elements without the necessity of visual control. As the grappler head lowers, an electronic sensing mechanism positions the grappler jaws directly over the element to be picked up. Because of the inherent strength designed into the 80-pound, 12-foot elements, they require a minimum of vertical support. This is the standoff pin, which provides positioning and vertical support on the reactor grid plate. When the fuel handling tests are finished, the mechanism will be dismantled and reassembled in the peat bottom plant, along with other components of the nuclear steam supply system. Construction on the prototype plant itself is moving forward rapidly and is scheduled to be in operation in 1964. But this is only the beginning. General Atomic engineers and scientists already are designing and developing larger H.T.G.R. plants, ranging in size from 150,000 to 1 million kilowatts. These large plants are expected to be truly competitive with conventional fossil-fueled power plants in many parts of the United States and of the world.